one here. So I'm going to solve another polynomial inequality, and this is going to be it. All right. So I am going to attempt to solve this fourth degree polynomial inequality. And to do that, I would like to get this thing zeroed out first. So I'm going to drag my 8x squared over the left side and also x cubed over to the left side. So how do I do that? I'm going to add x cubed to both sides. Subtract 8x squared from both sides. And when I do that to the right side of my inequality, of course, it will go to 0. So now my inequality is set to 0, and that's what we need. Next thing we need to do is try to completely factor this left side. Initially, it looks like I can factor an x out of all 4 terms, so I will do that. And then I ask myself, can I further factor down this 4-term polynomial left behind? Unfortunately, grouping will not work. You can kind of see that it just will not work out. And so in order to factor this down, we're going to have to tap into some of the skills we learned in chapter 3, namely the rational zero theorem, synthetic division, and the factor theorem and the remainder theorem. Okay, so therefore, I'm going to bring this polynomial off to the side of my paper, and I'm going to factor it over here. I'm going to form my list of potential rational zeros according to the rational zero theorem. P represents factors of the constant term -12. Q are factors of the leading coefficient +1. Factors of -12 would be positive -1, negative positive 12, positive -2, negative positive 6, and positive -3, and negative positive 4. Those are factors of -12. The only factors of a leading coefficient +1 would be positive -1. So my potential rational zeros are just going to be the numerator here, all these in the numerator, because all of these are going to be placed over positive -1. So we're just going to reduplicate the P list. All right, now we have to, using synthetic division, we have to choose amongst this list here in hopes of finding a 0. And we're going to synthetically divide it into the coefficients of this polynomial up here. Okay. Now, if you don't have a lot of paper and if you don't have an eraser, then you might want to just try a couple of these mentally before you actually, do the writing on the paper. So if I put 1 out here, try 1 from this list. 1 times 1 is 1. 1 plus 1 would be 2. 1 times 2 is 2. -8 plus 2 is -6. 1 times -6 is -6. 1 does not work. Try -1. -1. -1 times 1 is -1. 1 plus a -1 is 0. -1 times 0 is 0. -8 plus 0 is -8. -1 times -8 is 8. But these don't add up to 0. -1 doesn't work. I will try 2. 2 times 1 is 2. 1 plus 2 is 3. 2 times 3 is 6. -8 plus 6 is -2. 2 times -2 is -4, and these do not add up to 0. 2 doesn't work. Try -2. -2 times 1 is -2. 1 plus a -2 is a -1. -2 times -1 is 2. -8 plus 2 is -6. -2 times -6 is a positive 12, and we would get a 0 remainder. -2 is a 0. So we found one. All right, so we found a 0 of this polynomial, and therefore, if this is a 0, then x plus 2 must be a factor. Furthermore, we're going to leave behind, after factoring x plus 2 out of this, we're going to leave behind the trinomial 1x squared, minus 1x minus 6. And this can be further factored down using elementary methods from earlier algebra. Two factors of negative 6 that sum up to a middle coefficient of negative 1 would be negative 3 and positive 2. So this further factors in x minus 3 times x plus 2. Hence, ladies and gentlemen, we can come back up to our main problem and completely factor this polynomial here. We discovered negative 2 is a 0, so x minus a negative 2 or x plus 2 must be a factor. And this trinomial left behind further factors down into this. So the left side of this polynomial inequality has been completely factored. Okay. Any questions? How I completely factor that. Now we're going to find critical values. Critical values are values that send your factors to 0. So take each of these variable factors and set them equal to 0 and then solve for x to find these critical values. Now I have a duplicate x plus 2 factor here. We don't have to set it equal to 0 twice. So this is one of your critical values. This one will give us a critical value that's negative 2, and another critical value after solving this equation is positive 3. We're now going to put these values on the number line. Here's the number line here, and I got my negative 2, I got 0, and I got 3. And these numbers partition my number line up into 4 different intervals that need to be tested out with my inequality. All right, interval number 1. Give me something nice that's less than negative 2. A nice value less than negative 2. How about negative 3? Take negative 3, substitute it in here, 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 and here, and we have to verify if negative 3 is a solution to this inequality. Now, frankly, I don't really care what the actual number amounts to on the left when I put negative 3 in. I just care if the left is positive or negative because I'm comparing it to 0. So, ladies and gentlemen, you can speed this up a little bit. If you put negative 3 in here for x, you're going to have a negative. A negative 2 plus 2, a negative 3 plus 2 is going to give you a negative. Negative 3 minus 3 is going to be a negative. A negative 3 plus 2 is going to be a negative. When I multiply 4 negatives together, what do I get? I get a positive. Is a positive greater than or equal to 0? That's always true. So, true. Solutions will be coming from this interval. Let's test out interval number 2 now. Give me something nice between 0 and negative 2. How about negative 1? Let's let x be negative 1. Put negative 1 in here, 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 and here, and see if this negative 1 satisfies this inequality or is a solution. You don't actually have to put the negative 1 in here and actually get the actual number. We don't care about what number we get. We just care if the left side's positive or negative when x is negative 1. So I'll speed it up. If I put a negative 1 in here, I have a negative. Negative 1 plus 2 gives me a positive factor. Negative 1 minus 3 gives me a negative factor. Negative 1 plus 2 gives me a positive factor. When I multiply all these together, I'm left with a positive. And is a positive greater than or equal to 0? The answer is true. Solutions will be coming from this interval. Now we need to test out interval number 3. Give me some nice value that lies between 0 and 3. We could try positive 1. Let x be 1. Take 1, substitute it in here, 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 and here, and see if it is a solution to the inequality. Positive 1, put in here, makes the first factor a positive factor. 1 plus 2 makes this a positive factor. 1 minus 3, this is a negative 2, negative factor. 1 plus 2, this is a positive factor. So when you multiply a positive times a positive times a positive, you get a negative, and a negative is not greater than or equal to 0. False. No solutions will be coming from interval 3. Finally, interval number 4. Give me some nice value that's greater than 3. How about positive 4? Take 4, substitute in here, 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 and here, and verify. If I put 4 in here, my first factor is a positive factor. 4 plus a 2 gives me another positive factor. 4 minus 3 gives me another positive factor. 4 plus 2 is another positive factor. Multiplying all these positives together, you get a positive. Is a positive greater than or equal to 0? That's true all day long. So solutions will be coming from this interval. All right, the only other thing we need to ask ourselves is, would I include my critical values of 0, -2, and 3? Notice if you put 0 or -2 or 3 into this polynomial for x, the left side will go to 0. And is 0 equal to itself? The answer is yes. So we would include all of these critical values. So I'm going to include 0 and then shade to the left. I will include 3 and shade to the right. And you have the graph of the solution set to this polynomial inequality. Interval notationally, it's going to be from -infinity up to 0, including 0 in union with, including 3 up to +infinity. And we're done. Any questions how I solve that polynomial inequality?
I was just wondering how that's going to be on Alex. Are we going to have to do all of those steps on Alex with like the P over Q and all of that, or is it going to be a little bit different?
No, I mean, Alex is pretty much, you know, they might ask for the P over Q, especially if you get a question that, you know, breaks the problem down into several sub-steps. They may have you form the P over Q list, but most of the problems that I give you on Alex just want the answers, you know what I'm saying? So they don't want to see any work.
Okay, thank
You'll
you.
just do the work on separate paper. But I don't know, there might be a problem in your homework where it might be more interactive, where it kind of, you know, chips away at the problem step by step by step, and wants you to interactively, you know, engage with each solution for each step. But the majority of the problems are usually just answers. Okay. But do we understand the whole gamut here? How we went about solving that thing there? Okay. What slowed us down was factoring this 4-termer that grouping failed on. That's why we had to go and use our powerful theorems we learned in chapter 3 rather, to take care of and completely factor that down.
So
Okay.
the P over Q, is that just a way to factor?
P over Q is the list of potential rational zeros for this polynomial. P being factors of the constant term, Q being factors of leading coefficient. This is the rational zero theorem. Okay, that says that this list here would be the potential list of rational zeros for this polynomial. That is the rational zero theorem.
Yeah, and that gives you your factored form, right?
Yes. Yeah, and that ultimately enabled me to detect one of my zeros, and therefore x plus 2 must be a factor if this is a 0 by the factor theorem. And I know this is 0 because by the remainder theorem, we got a 0 remainder. So we're really tapping into all the theorems we looked at in chapter 3. And then we found our critical values, partitioned our number line up, and tested all the intervals to arrive at our solution set. Okay. All right, any other questions about this?
Yeah, I just had one more question. In the beginning of class, you had said that we are going to do an exam on chapters 2 and 3. Are we doing? I know we just did the quiz and exam on chapter 2. Is there more?
No. I meant 3 and 4. I apologize.
Oh, okay. That's why I was confused.
Yeah, the exam on chapter 3 and 4 will be released on March 23rd.
Okay. Thank you so much.
Thursday when we come back. All right. Any other questions about this here? Solving this polynomial inequality? All right, there's only one other inequality I need to demonstrate in this section to close it out, and that is solving what's called a rational inequality. So I'm going to dive right in. We're going to show you how to do that. So this is called a rational inequality because it's an inequality that contains rational expressions, and we wish to solve it for its solution set. All right, just like with polynomial inequalities, we want to get this thing zeroed out. And so what I'm going to do is I'm going to move this rational expression over to the left side by subtracting it. And then when I subtract it from the right side, I'm left with 0. So that's the first thing I want to do, is zero this thing out. All right, now the next thing I need to do is I need to consolidate these rational expressions on the left side of my inequality into a single rational expression. So to do that, I'm going to need a common denominator to actually subtract these. And my least common denominator turns out to be in need of a 4 minus x binomial. And also I'm going to need a 1 minus x. So that would be my least common denominator of both these denominators. The next step now is to build these fractions up into equivalent fractions that both take on the LCD. First fraction's got the 4 minus x, it's missing the 1 minus x. Because of that, top and bottom of the first rational expression gets multiplied by 1 minus x. Second rational expression's got the 1 minus x, it's missing the 4 minus x. So this second rational expression, top and bottom, gets multiplied by 4 minus x. Now we have to combine our numerators here. I'm going to distribute the 3 in here. And I'm going to distribute not a positive 6, but so we don't mess this sign up, I'm going to distribute a negative 6 in here. So therefore we have 3 minus 3x minus 24 plus 6x. And this all sits over our common denominator. All right, further simplifying the numerator, combining like terms, negative 3x plus 6x is 3x. 3 minus 24 is minus 21. All over my common denominator. All right, now I'm going to factor my numerator here. I can pull a 3 out of both terms here. All over my common denominator. All right, now I need to find critical values. And critical values are found by setting our variable factors in both the numerator and the denominator equal to 0. So don't bother setting 3 equal to 0. That makes no sense. So x minus 7 we set equal to 0. Solve for x, we get a critical value that is 7. So that's a critical value. Take 4 minus x in the denominator, set it equal to 0, solve for x. I'll add x to both sides. And this implies then that x would be equal to 4. There's another critical value. 1 minus x, set it equal to 0, add x to both sides, and we get another 0 as being 1. So these are our critical values. They are going to partition my number lineup into different intervals that need to be tested out with the rational inequality. So I got 1, 4, and 7. So I have 4 intervals to test out. Interval 1, interval 2, 3, and 4. And since the left side is being compared to 0 on the right side, my only concern is whether this expression is positive or negative when I choose values out of each interval. Interval number 1, I'm going to choose something less than 1. I'm going to let x be 0. Put 0 in here, 0 minus 7, this will be a negative. And a negative times a positive, the numerator will be a negative. If I put 0 in down here, I have 4 minus 0, that's going to be a positive. 1 minus 0, this will be a positive factor. So I have a negative divided by a positive, which is a negative, and is a negative less than or equal to 0? A negative, yes, is less than 0, so solutions will be coming from interval number 1. Interval number 2. Give me some nice value between 1 and 4. I'll just let x be maybe 3. Put 3 in here, 3 minus 7, that's going to be a negative factor, and a negative times a positive means the numerator will be negative. Put 3 in here, 4 minus 3 is a positive factor. 3 here, 1 minus 3 is a negative factor. What's this going to evaluate to? A negative divided by a negative is a positive. Is a positive less than or equal to 0? False. No solutions come from this interval. Interval number 3. I need a nice value between 4 and 7. I'll let x be 5. Take 5, substitute it in here in this factor. 5 minus 7 is going to be a negative factor, and a negative times a positive means my numerator will be negative. Put a positive 5 in here, 4 minus 5, this is going to be a negative factor. Put a positive 5 in here, 1 minus 5, this is a negative factor. A negative divided by a negative times a negative is going to be a negative over a positive, and a negative divided by a positive is a negative. Is a negative less than or equal to 0? The answer is yes. True. Solutions will be coming from that interval. Finally, I need to test interval number 4 out. I need something greater than 7. I'll do that over here. I'm going to choose x equal to 9, maybe. Put 9 in there, into this factor, 9 minus 7. This will be a positive factor times a positive factor. The numerator will be positive. Put a positive 9 in here, 4 minus 9. This will be a negative factor. 1 minus 9, negative factor. A positive divided by a negative times a negative is a positive over a positive, which is a positive. Is a positive less than or equal to 0? The answer is false. It doesn't work. No solutions come from this interval. All right, we're ready to put together our solution set now for this rational inequality. I have a question for you. Would we include any of these critical values in our solution set?
Yeah.
Would 7 be in the solution set? Well, it looks like it will. If I put 7 in for x, this will not be a 0 factor. 4 minus 7 is not 0. 1 minus 7 is not 0. So we're just concerned whether our denominator is 0, which it isn't if x equals 7. Notice the numerator, if I put 7 in for x, will become 0. But 0, although it's not less than itself, it is equal to itself. We must include 7 in the solution set. This will be included. Would I include 4 in my solution set? If you put 4 in here, here, and here, we have a big problem with this factor because this factor becomes 0 and the whole denominator becomes 0, and you cannot divide by 0, it's undefined. 4 is not in the solution set. Is 1 in the solution set? Well, if you put 1 in here, here, and here, then this factor gets into trouble. This factor becomes 0. 1 minus 1 is 0. You'll be dividing by 0. The whole thing is undefined. You cannot include 4 and 1 in the solution set, only 7. Okay, so therefore, I will include 7 with a bracket on 7, shade down to 4, but don't include 4, hence parenthesis. Don't include 1, shade down to negative infinity. That's the graph of the solution set of this rational inequality, here or here. Interval notationally, our solution set would be from negative infinity up to 1, but don't include, in union with 4, but don't include 4, up to 7, and include 7. And there you go, ladies and gentlemen, we are done. We have solved this rational inequality. So to recap very quickly, first of all, when you're solving a rational inequality, you have to get it zeroed out. That's the same thing that we have to do when we have a polynomial inequality. Secondly, if you have more than one rational expression on the left side, you must combine them into one rational expression. That means we had to get a least common denominator, equivalent fractions, and we had to consolidate the two rational expressions into a single rational expression. Then you factor all your numerators and denominators, set the variable factors equal to 0 to determine your critical values. Put the critical values on the real number line to partition it up into intervals that then will have to be tested out one by one with your rational inequality to see which intervals produce solutions. And then you put together your solution set. So with practice, ladies and gentlemen, you will get better at this. It does seem like quite a task here. It's a lengthy problem, maybe not difficult, but it does consume time and paper. There's no doubt about it. Okay. Now I will, I'll see if I can maybe make a small short video on how to solve polynomial or rational inequalities graphically using your TI-84. I don't really want to burn time in class because I'll never get through what I have to get through, but I might have a supplemental little video that I might attach to Canvas. If I come up with that, I'll let you know via email. All right, any other questions about solving this rational inequality here? All right, so just so long as you choose a real number from this interval or this interval, you will have a solution to your inequality. You choose any number in between here, it will not be a solution. or if you choose anything out here, it will not be a solution. Okay. All right, so that's going to close the door on section 3.7, and excuse me, 3.6. I just wanted to go over a couple more of those inequalities. 3.7 is the last section in chapter 3, the last one we're going to do. And so let's begin section 3.7. That is entitled Variations.
I had a question.
Yes.
Is the test over just section 3, or is it going to be over section 4 as well?
Well, it's also going to be over 4.1 on inverse functions. Okay. But that's the only section in chapter 4 it's going to be over is 4.1.
Are we going to cover that today, or are we going to do that?
I'm going to try, yeah, I'm going to try like heck to get through 4.1. Okay. All righty. Variations in 3.7. There's 3 types. You have what's called a direct variation. And a direct variations equation in general looks like this. K is a constant. It's called the constant of variation. It's just a number that has to be determined from experimental data. It's called the constant of variation, or sometimes it's referred to as the constant of proportionality. Okay, or it's called a proportionality constant. How do we read this equation? We say y varies directly as x. Y varies directly as x. Y is the dependent variable, x is the independent variable. This is called a direct variation. And the way a direct variation works is this way. If x's value increases, then this implies that y's value will also increase. If x's value decreases, then this implies that y's value will also decrease. That's a direct variation between x and y. I can think of an example. This is an example that I use with my face-to-face section. Suppose we have like a balloon that contains a gas. We have a certain volume of gas in this spherical balloon here. I have a question for you, ladies and gentlemen. If I heat this gas up inside the balloon, is the balloon's volume going to expand or contract? What do you think? If I increase the temperature of this gas?
Expand.
It's going to expand. So therefore, this is a golden example of a direct variation. We say volume is directly proportional to the temperature of the gas. V stands for volume, T for the temperature of the gas. If the temperature increases, the volume increases. If the temperature decreases, the volume will decrease. You could even try this at home. Take a balloon and blow it up, put it into your freezer and leave it in your freezer for about 3-4 hours. Come back and look at the balloon. You'll see that it has shrunk. Take the balloon out, put it on your counter, leave it on the counter for 2, 3, 4 hours, and you'll see that the volume then will increase. The balloon will then expand. That's a good experiment, very easy experiment, okay? That's a direct variation between x and y in general. We have another type of variation. It's called an inverse variation. And the equation of an inverse variation between y and x would look like this. You're noticing very quickly that these variations always contain this constant of proportionality, this variation constant k. Okay, this would be called an inverse variation between x and y. And specifically, how would we read this? We would read this way. We would say that y varies inversely as x. Y varies inversely as x. The way it works is that if x's value increases, then y's value will decrease. If x's value decreases, y's value will increase. That's an inverse variation or relationship that exists between x and y embodied in this equation here. A good example of an inverse variation in the real world would be, suppose that you hop on a hot air balloon and start ascending higher and higher into the atmosphere. Oh, by the way, you might not want to try this experiment in this day and age because we have a trigger finger for blowing balloons out of the air these days. Okay, so be careful on that one. So maybe not a good time to, do this experiment. Okay. But anyways, ladies and gentlemen, here's the ground. All right. If you get on a balloon here, and in your hand, if you have a barometer that can measure atmospheric pressure, the higher you go above the surface of the ground, the pressure will decrease. Okay. And there's no exception to that rule in the atmosphere. So I could say that the atmospheric pressure P is inversely proportional to the height above sea level that you are in your balloon. H is for the height above sea level. P is for the pressure. Pressure always decreases with height. So as my height increases, as I go higher and higher up in the balloon, the air pressure will decrease. If my height decreases, I come back down to the surface, the pressure will increase. Okay. That's a good example of an inverse variation out in the real world. All right. The last one is called a joint variation. Now, unlike a direct or inverse variation, a joint variation has more than one independent variable. Here's an example of a joint variation. Notice we have several variables here. We got Y is the dependent variable, W, X, and Z are independent variables. K is, again, the constant of variation. This is called a joint variation. And we could read this way. This would be read as saying Y varies jointly as W and X, and inversely as Z. So that's how you would read that equation. Y varies jointly as the variables W and X, and inversely as the variables Z. So it's interesting with joint variations because you can have a multitude of things going on here. W's value could be increasing, X's value could be decreasing, Z's value could be either increasing or decreasing. And it's interesting to see the interplay of how Y responds to the changing values of W, X, and or Y and or Z. Okay, that's called a joint variation. All right, ladies and gentlemen, let's have some fun. Let's go to our textbook and try to do a couple problems now. So, technology allowing, I am going to try to go to the textbook. And we're going to go to page 388. This is section 3.7. Section 3.7, variations. Notice it's the last section in chapter 3. We come a long ways in chapter 3. I'm going to dive on down, and I want to begin looking at problems like number 12 here. So let's go down to problem number 12. Notice the instructions for 11 through 20 say, write a variation model using K as the constant of variation. So let's try number 12. It says, simple interest I on a loan or investment varies directly as the amount A of the loan. So I and amounts are dollar figures. And what kind of a variation do we have here? Is this going to be direct, inverse, or joint? What do you think?
Direct.
It's going to be a direct variation. And it looks like I depends upon what? The interest depends upon the amount of money that's in the that you invest in the loan. So I is equal to K times A, and this would be your answer. This would be the variation that you would write for problem number 12 there. Can we see that there? Interest varies directly as the amount of money that you invest in a loan. That's your answer. That's it. That's all they wanted for number 12. That's a direct variation between interest and amount. Number 13, interesting. It says the average cost per minute, denoted as C with a little bar above it, for a flat rate cell phone plan is inversely proportional to the number of minutes used. And is this a direct, inverse variation, or joint variation? What do you think? kind of a variation we got here? Well, you see the word inversely in here. Therefore, it must be an inverse variation. So the average cost is inversely proportional to the number of minutes that the phone is used. So C bar is going to be equal to K divided by N. So this would be the equation you would write to represent that inverse variation that exists between average cost and the number of minutes the phone is used. Notice when you see the word inversely, you're always going to have a variable in the denominator of a fraction. If you don't see the word inversely anywhere, you'll never see a variable appearing in any denominator of a fraction. That's the answer for number 13. All right, number 15. This problem involves a right circular cylinder, and I am going to draw a picture of a cylinder. A right circular cylinder is a glorified name for basically a can. The can has a certain height to it. This would be the height, H. And it has a circular bottom and top, so circles always have radii. So this would be the radius of the circular top or bottom. According to number 15, the way it reads is, it says, the volume V of a right circular cylinder varies jointly as the height H of the cylinder and as the square of the radius of the cylinder. How are we going to write this joint variation using an equation? Well, volume V varies jointly as the height H of the cylinder, and the square of the radius. And there you go. This would be the equation that represents that joint variation between volume, the height of a cylinder, and its radius squared. Okay. Any questions about that? All right. Another one like number 15.
I had a question.
What's that?
I had a question. So
Go ahead.
in the joint equation you gave us, it was y equals kwx over z. Why is it not over anything?
Okay, very good question. Let's go back and read it again, number 15. In number 15, do you see anywhere where do you see the word inversely anywhere in here? Inversely. No, you never see the word inverse or inversely. Because of that, you'll never see any variable appearing in any denominator of a fraction. Does that make sense? You got to see the word inversely in there.
Yeah.
That's why you don't see any variable downstairs. Okay, that's number 15. Let's see what else we got here. Okay. Now you're probably wondering, how do we find this constant of variation K? Well, we need to have data. So let's move on down to problems 21 through 26 in your textbook, where it says find the constant of variation K for all these problems here. I'm going to try number 22. Number 22 says P is inversely proportional. Oops, wrong problem. Number 22. M varies directly as X. When X is 10, M is 42. They want us to find K, the variation constant. First, we have to write the variation. So M varies directly as what? X. That suggests my equation would be M is equal to what? K times X. That is representing that M is directly proportional to X. Now, to find the variation constant K, we need data. Oh, but in number 22, they give us data. They tell us that when X equals 10, M is 42. I think we have enough information now to solve for K. I'm going to replace M with 42, drop in 10 in place of X, and therefore we have an equation that we can now solve for K. Solving for K, we divide both sides by 10, and therefore this implies that our constant of variation is going to be 4.2. And there you go. We have solved for K. If you want to, you don't have to do this for this problem. They just wanted K, but if you wanted to write the specific variation now, you would say that M is equal to 4.2 times X. There you go. Any questions how we found K? All right, that was number 22. All right, maybe we could try another one here. Number 24, T is inversely proportional to X. When X is 50, T must be 200. Find K. First, we have to write this as a variation, and this is an inverse variation between T and X. So therefore, to write T is inversely proportional to X, we would say T is equal to K over X. There you go. There's your inverse variation between T and X. T is inversely proportional to X. That's what that's saying. Now to find K, we need experimental data. And here it is. They tell us that when X is equal to 50, this would imply that T would be 200. Now we have data, so we can find the value of K. In for X goes 50, and in for T, we drop 200. So we have 200 is equal to K over 50. And now I have to solve this equation for K. So how do we solve for K? Multiply both sides by 50, and K is equal to 50 times 200, which nets us 10,000. So K is equal to 10,000. That's it. That's what K would be. If you want to also write this variation specifically, it would be T is equal to 10,000 over X. There you go. Any questions how we're finding K? Given data. Right. All right. Okay, ladies and gentlemen, I'm going to have you try a problem now. Classwork number 1, we can call this. Problem number 25. It says Y varies jointly as W and V. When W is 40 and V is 0.2, Y is equal to 40. Let's use that data to find K. So go ahead and do problem number 25. First, set up the variation, plug in the numbers where they belong, solve for K. Okay, number 25, classwork number 1. All right, ready to look at number 25? Says y varies jointly as w and v. Nowhere do you see the word inversely in here. So you're not going to see any variables in any denominator of any fraction. So y varies jointly as w and v. So the equation would be y is equal to y would be equal to k times wv. Y varies jointly as w and v. They tell you w, when w is 40, v is 0.2, y is 40. So we plug those values in where they belong and then solve for k. And I do get k is equal to 5. Anybody get 5 for k?
Yeah.
All right. So do we understand how we're finding that constant of variation here by using data? All right. First, you got to write the variation, substitute the given data into where it belongs, and then solve for k. That's all there is to it. Okay. All right, that's classwork 1. All right, let's go back to our book here. Okay, let's see here. Now, let's see the next one here. All right, now as you go down in this section in the homework problems, or actually the textbook problems, and you're welcome to do any of these for homework for extra practice. I do post the solutions. I'm going to do number 36 here. They do become more wordy, as you can see. Number 36, the area of a picture projected on a wall varies directly as the square of the distance from the projector to the wall. A, if a 15-foot distance produces a 36 square foot picture, what is the area of the picture when the projection unit is moved to a distance of 25 feet from the wall, 10 feet further back from the wall? I got a question based on your experience. If you had a flashlight showing, shining on a wall, and you move further and further back away from the wall, does the circle, the projected image on the wall, get larger or smaller? What would be your thinking? If you have a flashlight shining on a wall and you move further back away from the wall, does the picture that's on the wall, does the projected image become larger or smaller?
Larger.
It gets larger and larger and larger. Okay. So we can draw a picture of this maybe. We have our projector here. And here's my projector. And it basically sends out rays of light that diverge from each other, move further and further apart, further to get from the lens. Here's my wall. And let's say this is my picture here. And you got a ray that comes down here also. And you got a ray that also goes up here. Okay. So there would be the projected image on the wall. And ladies and gentlemen, you can see that if you were to move the projector back further from the wall, that this image is only going to get what? Larger and larger and larger. Okay. The image is going to get larger and larger. Is this making sense? The further you go away from the wall with the projector, the image keeps getting larger. Okay, that's the idea behind this problem, number 36 here. Now, it says, therefore, the area of the image on the wall, this is the area right here. The area of the image on this wall, they say is what? Is it inversely proportional or directly proportional? Let me go back and read it here. Oh, it says the area varies directly as the square of the distance that the projector is away from the wall. So this will be the distance that the projector is away from the wall. We'll call it D. So the area of this projected image is directly proportional to the square of this distance here. So A is equal to K times D squared. That would be your variation you have to write as an equation. And now we're in business. For part A, they indicate if the distance from the wall, between the wall and the projector, is 15 feet, they indicate that the area of the projected image is how many square feet? Oh, what was that? 36 square feet? They want to know, okay, if I pull this projector 10 feet even further away from the wall, So it's then 25 feet from the wall. What would be the new projected area of the image on the wall? That's what they want to know here. Okay, to do this problem, what's the first thing we need to find? What do we got to find first? We must find the what? The value of, we got to find K. In order to find K, we're going to use this data right here. So here we go. In for the area goes 36. And I'm actually going to put the units in also. If you get into the sciences or in any sort of engineering, you also got to pay attention to your units. Your units have to work out just as well as your numbers. So in for the distance goes 15 feet. All right, so we got 36 feet is equal to K times, what's 15 feet times 15 feet? I believe it's 225 square feet. To find K, I'm going to have to divide 36 feet by 225 square feet. Notice that the units of feet in the numerator cancel out with one of these units of feet in the denominator. And so what we're going to have is we're going to have 36 over 225 times 1 over feet. Right? Now, why don't we just convert this to a decimal? What's 36 divided by 225? Anybody? 36 divided by 225. That gives me 0.16. So I'm going to call it 0.16. And the units are going to be 1 over feet. All right, so that is my constant. Therefore, my specific variation becomes area is equal to 0.16 times d squared. Now we can answer the question. The question is, if we pull that projector back 10 feet further from the wall, so it's now 25 feet from the wall, what would be the area of the projected image? Well, area, we're going to solve for. This is 0.16, and the units are 1 over feet. I'm going to show you how the units work out here. Times the distance is now 25 feet, and we have to square that. What's 25 feet times 25 feet? Well, I believe that's going to give us 625, so 625 square feet. All right. Wait a minute here. Something is wrong. Oh, you know what I forgot? What did I forget, ladies and gentlemen? I blew it. What kind of units does area have to be here? Not just 36 feet, but 36 what? That should be square feet. Okay, so this should be square feet, square feet, square feet. So square feet over square feet, basically the units just drop out of the picture. There are no units. Units are gone. So it's just going to be 0.16. So your constant of variation is a dimensionless or unitless number. That's all it is. So there are no units attached to K. All right, so we're going to have 0.16 times 625 square feet. And what is 0.16 times 625? That gives you 100. You got your answer. So if you move that projector 25 feet back from the wall, the area of the projected image will grow to 100 square feet. That's going to be the area. Makes sense. And when the projector is 15 feet from the wall, the area is 36 square feet. So it's grown from 36 square feet to 100 square feet when we basically have increased the distance by 10. Notice this is not a linear relationship between area and distance. So it's a square. It's a square or quadratic relationship between area and distance. In the sense that if you increase the distance by 10 feet, the area does not increase by 10 feet. It increases much more than that. Because this is not a linear relationship between area and distance. It's a quadratic relationship embodied by that direct variation there. Okay. Any questions how I did that problem there? 36, and that was all 36A here. There is a part B to this question, I believe. And in part B, it says if the projected image is 144 square feet, how far will the projector be from the wall? So now it says if the area of the projected image is 144 square feet, what is the distance from the wall? Well, let me ask you this, ladies and gentlemen. Do you think that the distance has to be greater than or less than 25 feet if the projected image is 144 square feet? What do you think?
Greater than.
It's got to be greater than, because when we were 25 feet away from the wall, our projected area image was 100 square feet, but now it's 144 square feet. So when I get done solving for distance, it had better be larger than 25 feet, or else we made a mistake somewhere. All right, so anyways, using our direct variation that we created in part A, and here it is again. So using this, we can answer this question. In for the area goes 144 square feet. That's equal to 0.16 times the distance is unknown. We have to solve for distance D. To do that, we divide both sides by 0.16. And what is 144 divided by 0.16? 144. That's 900. So therefore we have 900 square feet. Notice the units are still square feet, because there were no units attached to our constant K. So 900 square feet is equal to distance squared. To solve for distance, we take the square root of both sides of our equation. Hence, the square root of 900 square feet reduces us down to just 30 feet. Yes, when you take the square root of square feet, the square feet just become linear feet. And those are the proper units for distance, 30 feet. So the projector will have to be 30 feet away from the wall. So do you see how the units are working out too? The units have to work out just as nicely as the numbers. And whenever you do any sort of scientific or engineering calculation. So units are very important to pay attention to, because if your units are not coming out correctly, that means you probably are not putting the numbers in the right place, or you're not, using the formula correctly. All right. So you always got to check your units. Any questions about that one? And this was part B of problem 36. Okay. All right, classwork number 2, ladies and gentlemen. I want you to do problem number 44. Let's read it. It says the strength of a wooden beam varies jointly as the width of the beam and the square of the thickness of the beam, and inversely as the length of the beam. A beam that is 48 inches long, 6 inches wide, and 2 inches thick can support a load of 417 pounds. Find the maximum load that can be safely supported by a board that measures 12 inches wide, 72 inches long, and 4 inches thick. We will assume it's the same type of wood. That's the key assumption. We're not going to some other material. Notice we do have our variables here. I want you to, keep these variables: L for length, W for width, T for thickness. The first thing you have to do, ladies and gentlemen, is you have to write the appropriate variation that addresses what's being read in the reading here. Then you're going to have to use some data that's given to solve for K, and then you can answer the question. All right, go ahead and work on that problem. This is classwork number 2, number 44. Classwork 2. Okay, go ahead and do that problem. I'll give you All right, let's check it out, see how we're doing here. Now, number 44, I used S for strength, okay? So this is gonna be the equation that represents that joint variation. The strength of the wood beam is directly proportional to the width and the square of the thickness and inversely proportional to the length of the board or the beam. They give us data. We're gonna have to feed this data into here to solve for K. So I put all the numbers in where they belong, and I left the units in there to show you how the units work out too. You go through the numbers, 6 times 4, this becomes 4, is 24. 24 over 48 is 1/2, 0.5. Notice the units, we got inches times square inches is cubic inches, but cubic inches divided by inches reduces down to inch square inches. Notice the units. Dividing both sides by 0.5 square inches, K walks out with a value of 417 over 0.4 over 0.5 square inches, which I actually divided 417 by 1/2 and got 834. Notice the units on K, pounds per square inch. That's called pounds per square inch. Now we can answer the question. What would be the strength of a board or a beam, same material, that's the key assumption, that measures 12 inches in width, 72 inches long, and a thickness of 4 inches? Well, now we can put the values into our more specific joint variation. I put all the units in here to show you how the units work out. Notice pounds per square inch times inches times square inches. So inches times square inches is going to be cubic inches. So we're going to have pounds, cubic inches over square inches, but the square inches cancel out and leave behind only 1 inch up here, 1 inch unit up here. So we're going to have pound inches over 72 inches. So when you take 834 times 12 times 16, you get 160,128. Divide that by 72. Notice the units of inches cancel out here, leaving you with proper units for strength, pounds. See how the units work out perfectly here? We're left with pounds for units. Did anybody get 2,224 pounds of strength?
Yes.
All right, so that beam can support a little over 1 ton of weight now. Over
Can you
1
go
ton.
up? Can you go up for a sec? Okay.
So the units have to work out just as nicely as the numbers have to work out. And if your units are not working out, that's an indication that something's wrong. That's why if you get into the sciences or into engineering, you got to pay very close attention to your units and make sure they're working out. So units are critical. There it goes for chemistry, physics. I don't care what kind of science it is, or engineering. You're always going to be working with some sort of units. All right. So the nice thing is this is recorded, so you can go back and mull over this, you know, at your leisure. And you can even look at this all week next week when you're off if you want. Just kind of invest all your time in just observing this if you want. It's up to you. Okay. All right, so that's number 44. That was classwork number, what was it, 2, I believe? Okay, ladies and gentlemen, we're going to close the door on that section now because we're running out of time. So the last section here is 4.1. It's entitled Inverse Functions. What's the inverse of multiplication? That would be division. The inverse of addition is subtraction. Operators have inverses, you know, functions have inverses too, but not all functions have inverses. So what functions do have inverses? Well, I'll let you in a little secret here. In order to possess an inverse, a function needs to be 1-to-1. So this is a very important fact. Only 1-to-1 functions have inverses, 1-to-1. Sometimes we abbreviate these words 1-to-1. We just say 1-1. That means 1-to-1. So only 1-to-1 functions have inverses. All right, so what's the definition of a 1-to-1 function? one-to-one function. Do not have any repeated y coordinates. For any two different ordered pairs. All right. Or points. Now, the easiest way to determine if a function is one-to-one is to look at the graph. So a graph of a function that is one-to-one passes a very simple test. Passes what is called the horizontal line test. Didn't we have another test which was a line test? It wasn't the horizontal line test, it was called the vertical line test. Anybody remember what that vertical line test was able to tell us? I know that was a ways back, but does anybody remember the vertical line test?
If it was a function or not?
What's that? Yeah, we used it to determine if a relation was a function or not. Well, there's a horizontal line test that says that if a function passes this horizontal line test, then the function is one-to-one, meaning it would possess an inverse. Okay, it's a very easy test to administer, just as easy as the vertical line test. Suppose I have the graph of a function, and the graph of my function looks like this. Okay, now I'm going to subject its graph to the horizontal line test. That is to say, I'm going to take a horizontal line, and no matter where I place that horizontal line in the XY plane, no matter where you place it, if the horizontal line touches the graph or crosses the graph in at most one point, then it's enough to say that the function is a one-to-one function. And notice, no matter where I put a horizontal line, I cannot make a horizontal line touch or cross this graph at more than one point. So this is an example of a one-to-one function. So this function would possess an inverse. Suppose I have the graph of a function that looks like this. Would this function be one-to-one? This is not one-to-one because I can put a horizontal line somewhere, maybe like right here, and that horizontal line would touch the graph in more than one point. This is not one-to-one. In fact, there's several points on this graph that possess the same y coordinates. Do you agree? There's 4 of them here. All have the same y coordinate because they lie on a horizontal, right? So this graph passes the horizontal line test. This graph fails the horizontal line test. So do we understand the horizontal line test? That's all there is to it. Right? It can basically just tell us if a function is a one-to-one function or not. Now, some functions are not given to us in the form of a graph. I mean, if we have a function represented as a set of finite ordered pairs, we should still be able to determine based on the definition I gave you as to whether this is one-to-one or not. So is f one-to-one? Is this a one-to-one function?
No.
Not one-to-one. Why not? Why is that not one-to-one?
There's 2 forms.
Yeah, it's not one-to-one because we have 2 different points for the function that possess the same y coordinates. Okay, so because we have repeated y coordinates, this is not one-to-one. Now, here's a very important theorem that enables us to determine if 2 functions qualify as being inverses of each other. This is a theorem, and it actually makes use of the composition operator. Remember when we were studying algebra of functions, we had something called a composition operator. And basically this theorem says this: let f be a one-to-one function. So automatically we know that, if the graph of this function passes the horizontal line test, we say that G is the inverse of function f. In other words, g is equal to f inverse. This is read as, this is not to be read as f to the negative 1 power. This is read as f inverse. G is the inverse of function f, f inverse. If and only if and only if means this theorem is a two-way street. So not only is it true the way we read it, you know, from left to right, but it's also true if you read it backwards. So the converse is also true. If and only if, what must be true? Well, here's what must be true. If f composed with g of x is equal to g composed with f of x, and both of these can be shown to give you x, then it's enough to say that g is the inverse of function f, okay? Or g and f are inverses of each other. So this theorem can be read, like I said, in both directions. One way to read it is to say that if function f and g are inverses of each other, then their compositions must both yield x. Or this theorem can be read backwards, meaning that if we can show that these compositions both yield x, then it's enough to say that g and f are inverses of each other. So that's an if and only if two-way street theorem. Well, that's pretty neat. So this composition between the functions is enough to tell us whether functions qualify as being inverses of each other. So that's very useful there. Maybe we can put it to work and try it out on an example. Okay. So let's see if we can try this out. Suppose that we're given two functions. The first one's a linear function. It is written as 100 plus 12x. And suppose another linear function is g of x, which is x minus 100 over 12. So both of these are linear functions. And the question is this: are these inverses of each other? Now, let's just kind of look at these functions. Does it kind of look like they are inverses in a way? What's the inverse of adding 100? The inverse of adding 100 is subtracting 100. What's the inverse of multiplying by 12? Dividing by 12. You know, it kind of seems intuitively like these might be like inverses. They undo each other. Well, let's put it to the test. Let's look at the compositions. Let's look at f composed with g of x. F composed with g of x is the brand new function called f of g of x, which means it's going to be f taking on the value of g of x being x minus 100 over 12. So x minus 100 over 12 now becomes the input in the function f. So this expression comes up here and drops right in for x in the definition of function f. So the function f evaluated x minus 100 over 12 is going to be 100 plus 12 times x minus 100 over 12. But what happens to the 12s here? These 12s cross reduce out, and we're left with 100 plus x minus 100. Oh, but what happens to the hundreds? They drop out. So we're left with what? We're left with x. So we have shown that f composed with g of x is equal to x. Everybody see that there? That's still not good enough to, you know, say that f and g are inverses of each other. We have to look at the other composition now, g composed with f of x. We've got to spin this around. Well, g composed with f of x is g of f of x. That's to say, if I put function f of x into function g, I will be evaluating function g at 100 plus 12x. This 100 plus 12x now has to come up here and take the place of x in the definition of function g. So I have to put 100 plus 12x in right here. So 100 plus 12x minus 100 over 12. Oh, but look, the hundreds drop out. And we're left with this. Oh, but look, the 12s reduce and we're left with x. Ladies and gentlemen, I have shown that both f composed of g of x and g composed with f of x both yield x. Therefore, by the theorem that was mentioned above, these functions are inverses of one another. So they're inverses. Everybody see how I applied that theorem above there? They're both inverses of each other because we've shown that both compositions are X. So F and G are inverses. They're inverses. Kind of look like they were inverses anyways. All right. How do we find inverses? How to find an inverse? Suppose we have a one-to-one function, and I want us to actually find the inverse. Well, these are the steps you want to consider. Step number one, you always want to replace functional notation with y. And the reason why that is because y just looks nicer, it's simpler looking than f of x. Number two, then what we need to do is we need to interchange x and y. X is replaced with y is replaced with x. We have to interchange the roles of these variables. Once we do that, then we have to solve for y. And last but not least, we then replace y with appropriate inverse functional notation. And if our original function was f of x, we replace it with f inverse of x. If our original function was g of x, we would replace y at the end with g inverse of x. G inverse of x. Okay? Just depends what notation you're using here. In general, these are the steps, ladies and gentlemen, you want to pursue in order to find the inverse of a function. It's those steps you've got to walk through. Now let's see if we can apply it to an actual example here. All right, so those are the steps. Okay. So here's a classic typical problem that you'll be confronted with in the near future. It'll say find the inverse of this function f of x, which is 3 minus x over x plus 3. Now this is a rational function, and if you were, ladies and gentlemen, to graph this function quickly using your graphing calculator, you would discover that it would pass the what test? If it's 1-to-1, it's got to pass the horizontal line test. Do you agree? And I just want to see if I can. Whoops. I want to see if I can show you very quickly using Desmos here. Okay. All right, I just graphed it very quickly by using the Desmos calculator, and you can clearly see that this rational function is indeed a one-to-one function, because nowhere can you put a horizontal line anywhere and have it touch the graph at more than one point. Notice the horizontal asymptote is y equals -1. Even if you put a horizontal line right through y equals -1, it will never touch that graph, because the graph becomes asymptotic with respect to the horizontal asymptote, but never touches it or crosses it. Certainly at more than one point. I don't think it doesn't cross it anywhere. And we do have a vertical asymptote, just in passing, noting at -3, x equals -3, we have a vertical asymptote. We know all about that stuff, though. We went through rational functions. All right, so it is 1-to-1. Okay, so it must have an inverse. How do we find it? First, we replace f of x with y. Then we swap x and y. Y becomes x becomes y. Now we have to solve this for y. We must solve this for y. To do so, I'm going to multiply both sides by y plus 3 to get rid of the fraction on the right. If I multiply the right side of this equation by y plus 3, the y plus 3's would cross cancel out, leaving me with 3 minus y. Do you understand how I went from here to here? I multiply both sides of this by y plus 3. Distributing, I have xy plus 3x is equal to 3 minus y. Factoring, I need to get these terms together to both have y in them. I'm going to add y to both sides and take the 3x over to the right. So I'm going to take this over to the right, and I'm going to take this term over to the left. To do that, I add y to both sides. And to take the 3x over to the right, I subtract 3x from both sides. After doing that, my equation now looks like this. Now I can factor y out of both these terms. And now how do I solve for y? I divide both sides by x plus 1. And I got it. So therefore, y is equal to 3 minus 3x over x plus 1. Last step is to replace y with appropriate inverse functional notation. And since my original function had f of x, I must replace y down here with f inverse of x. So f inverse of x is, you are looking at it, 3 minus 3x over x plus 1. This is the inverse function right here. This is the inverse function of this guy. These are inverses of each other. Inverses. Any questions how I found the inverse of function f of x by going through these steps here? Okay. All right. Suppose I give you function f is defined to be this set of finite ordered pairs here. Is this function 1-to-1? 1-to-1.
Yes.
Yes. Is it even a function? I'm calling it a function. Hey, how do I even know? Might just be a relation. How do I know this is even a function? Because we don't have any duplicate what coordinates? All the x coordinates are unique. That's why this relation is a function. And it's a 1-to-1 function because all the y coordinates are unique. What would be the inverse function of this function denoted as f inverse? We read this as f inverse. You do not read this as f to the negative 1 power. You read this as f inverse. You know what the inverse function does to the points that lie in the original function? It basically just interchanges the x and y coordinates. So if 1, 3 is a point on the original function, then 3, 1 must be a point on the inverse function. If 2, 5 is a point on the original function, then 5, 2 must be a point on the graph of the inverse function, etc., etc. 3, 10 becomes 10, 3, 4, 10 becomes 10, 4. I'm sorry, 4, 20 becomes 24. This is a pictorial way of representing a function and its inverse. The first set, it represents the domain of function f. This is the domain of function f. And this set here is the range of function f. 1 gets mapped to 3, 2 to 5, 3 to 10, 4 to 20. The inverse function reverses the role. It takes 3 and maps it back to 1. 5 gets sent back to 2, 10 gets sent back to 3, 20 by the inverse function gets sent back to 4. Notice what happens with the relationship between the domains and ranges of the function and its inverse. As it turns out, the domain of function f is really equal to the range of the inverse function. And the range of the inverse function is equal to the domain of the inverse function. So the domains and ranges interchange roles between a function and its inverse. Okay. Furthermore, I want to show you this here. What if I had, I'm going to try something here. What if I had f of f inverse of 3? Well, f inverse of 3 takes 3 and sends it back to what? 1. So this is f evaluated at what? 1 then. But f takes 1 and maps it back to 3. Interesting thing occurs here, ladies and gentlemen. It's kind of like f and f inverse kind of like nullify each other, kind of cancel each other out. And what drops out of this madness is just 3. Pretty interesting, isn't it? You see that there? Well, you can spin it around. You could say f inverse, what would be f inverse of f of 4? Well, what's f of 4? F of 4 is 20. So 20 becomes the input in the inverse function. But what is f inverse of 20? Well, the inverse function takes 20, maps it right back from whence it came, back to 4. So that's equal to 4. Look at that. F inverse of f of 4 is just 4. So in a crude sense, it's kind of like the f inverse and the inverse function of f and f kind of like cancel each other out. It just leaves you with whatever number, is the argument. We'll point that out there. That's pretty interesting to see. But the main idea here is that the domains and ranges of the functions interchange roles between a function and its inverse. That's important to note. Okay. All right, we're in the home stretch, and it is 2:03. Suppose I want to find the inverse of f of x equal to x squared plus 4. I'll tell you what, let's graph this quickly. Using the parent function f of x equal, or g of x equals x squared, what kind of transformation has this function undergone? What transformation has the graph of the basic parent function x squared of g of x equals x squared undergone? Looks like the graph has been shifted, upwards 4 units. So the vertex point, instead of being at the origin, is now at 0,4 here. And that would be a quick sketch of the graph of f of x equals x squared plus 4. Does this graph pass the horizontal line test? Doesn't work. Doesn't pass the horizontal line test. So this function is not one-to-one. Well, wait a minute. If it's not a one-to-one function, then it does not have an inverse. Then why am I saying find the inverse? Well, as is, this does not have an inverse. Can we force it to have an inverse? The answer is yes. But in order to do so, we're going to have to restrict its domain. So what we're going to do is we're going to restrict the domain of the original function. By restricting the domain, we can force this to be a one-to-one function. Presently, my domain is from negative to positive infinity. Negative infinity to positive infinity. I'm going to restrict the domain to consist of only non-negative real numbers. When I do that, the left branch of this parabolic graph disappears. It's gone. And so the graph of this now one-to-one function, whose domain has been restricted, is going to look like this. Now this is a one-to-one function. And so therefore it will now possess an inverse. So by restricting the domain, I force this original function, which was not one-to-one, become one-to-one. And now we can find the inverse here. So how do we find the inverse of this now? Replace f of x with what? Y? Interchange x and y. Y becomes x, x becomes y. And now we got to solve for y. Must solve for y. Subtract 4 from both sides. I'm going to spin this whole thing around here. And then I have to take the square root of both sides. But when I take the square root of the right side, do I consider just the positive square root, the negative square root, or both? Oh, wait a minute. What's the range of my original function? The range of the original function, or the function where the domain has been restricted, is from 4 to infinity. That's the range, correct? The range being y coordinates. So what must be the domain of my inverse function? The domain of my inverse function that I'm trying to find must be equal to the range of the original function. So this must be the domain of my inverse function. And what must be the range of my inverse function? Well, that must be equal to the domain of the original function, whose domain is this guy right here. Aha. And so now, ladies and gentlemen, since the range of my inverse function must consist of non-negative real numbers, cannot consist of any negative numbers, would I take the positive or negative square root of the right side? What do you think? When I solve for the y here. Positive or negative square root of x minus 4 if the domain of my inverse function is to consist of only non-negative real numbers. What do you think? Positive or negative square root? What do I do here? Positive or negative square root? Well, it's got to be the positive square root. Because the range of my inverse function is to consist of all numbers that are not negative. Okay. Therefore, y is equal to positive square root of x minus 4. We have our inverse. Going to inverse notation, f inverse of x, therefore, is equal to the positive square root of x minus 4. This is your inverse. And this is the domain and range of my inverse function. Any questions how I found the domain? Excuse me, how I found the inverse of this quadratic function here? By first restricting its domain so that it's 1-to-1. And then going through the steps I laid out several pages back, how to find the inverse. And then realizing that when I take the square root of the right side of this equation, it must only be the positive square root because the range of my inverse function must consist of only non-negative real numbers. So you don't have the negative sign in front of the square root here, only the positive sign. So you got to pay attention to these domains and ranges for a function that's inverse. Because you're going to try to find the inverse. All right, that making sense? So I found that there, that inverse function. Okay. I just have one more classwork for you. We'll call this one for the road, okay? Last classwork. Now, you don't need a piece of graphing paper to graph this. You can use a piece if you want, but it's not necessary because I think you'll get the idea as to how to do this, despite maybe not using graphing paper. Suppose that I give ourselves the graph of some function f, and let's say that it looks like this. Let's suppose the graph of some function f looks like this here. And I'm going to give you these 3 key points here. This point down here is -4, -2. This point up here is going to be negative -3, +2. And this point here is going to be 0, 4. What I want you to do is I want you to graph the inverse function. So this is some function f here. I want you to graph the inverse of this function. Just sketch the graph. Okay. So see if you can do that, Liz. I think that you can do that based on what I've shown you here about a function and its inverse. What happens to the x and y coordinates. See if you can maybe sketch the graph of the inverse function there. Okay, so what does a function do to the points that what does an inverse function do to the points that lie on the graph of the original function? Well, here's the graph of the original function f, and what the inverse function does is just interchange the x and y coordinates. So -4, -2 on the point on the original graph becomes the point -2, -4 on the graph of the inverse function. -3, 2 becomes a point. 2, -3 is a point on the inverse function. 0, 4 becomes a point. 4, 0 as a point on the inverse function. So all you gotta do is just plot those new points, and you get this graph here. I also want to point one more thing out, the graph of a function and its inverse function is always symmetric with respect to this line y equals x. That's always going to be true. You'll always have that perfect symmetry between the graph of a function and its inverse function, in the sense that if you folded the paper about this line y equals x, this graph would mesh up perfectly with this graph here. So these points would mesh up perfectly, these points and these points here. And like I said, graphing paper should probably be used to see that symmetry more clearly, but that's always true when you graph a function and its inverse. You always have that symmetry with respect to the line y equals x there. Okay. For instance, let me just show you this last problem here. If I had y is equal to like 3x plus 2, and I want to find the inverse, this is going to be a one-to-one function. It's just a linear function with a slope of 3 and a y-intercept of 2. What would be the inverse? So we basically interchange x and y, and we just solve for y. So we're going to have subtract 2 for both sides, divide both sides by 3, and we have the inverse. So therefore, the inverse is x minus 2 over 3. Right? So, and if I call this function f of x, then I would call this guy f inverse of x. So these are inverses of each other. This function here is the inverse of this function here. Okay. Now, you can clearly see that if I was to graph both these functions, you'll see that they do possess that symmetry with respect to y equals x. And so what I'm going to do is just go to, you can do this on your TI-84 calculator, or you can use the, this Desmos calculator, which is really fabulous here. And so I'm going to try this here. So I'm going to graph the original function, y equals 3x plus 2. And here comes the graph of the inverse function. Maybe I should have called this guy f of x up here. All right, and then I'll call this one f inverse of x. And it doesn't like the notation up here, so all right, whatever. I'll just call it g of x. Okay, and then what I'm going to do is I'm going to graph that line y equals x so that we can clearly see the symmetry. So y equals x. And you can see that, yes, these graphs are perfectly symmetric with respect to this line y equals x here. And that's true. Whenever you graph a function and its inverse, you'll always have this symmetry with respect to the line y equals x. All right. Okay, ladies and gentlemen, I think I've worn out my welcome here. Now, again, I will move the exam on chapter 3 and 4 to Thursday, March 23rd. When we come back, I will release it. So on March 21st, I'm just going to lecture over the material that I was supposed to lecture on March 23rd. I will open up all the homework that needs to be opened up. Any quizzes that need to be opened up, I will open up those. And I hope you have a great break. Hopefully you have a safe break, and try not to forget all your math. It's always wise maybe somewhere in there to just kind of review things a little bit if you're able to do so. So with that, I will let you go. Okay, I'll stay on the line if you have any questions for a couple minutes. All right, so take care.